Hi, my name is Kay, and I'm a second-year PhD student under Dr. Garces at University of Hawaii. I'll be presenting on explosion yield estimation using machine learning methods. This is a collaborative research project with Dr. Kim from Lawrence Livermore National Labs. We used convolutional neural networks to estimate explosion yields and height of detonation from acoustic explosion data. The results are further analyzed by breaking down the accuracy metrics into subcategories. Explosion yield estimation from acoustic data is traditionally computed through parametric overpressure models using low-frequency waveform features. Even with the rise in popularity of machine learning, it has yet to catch on with yield estimation, mainly due to the lack of data. With access to a relatively large explosion dataset, we implemented a machine learning method as proof of concept. This will also provide future insight for our growing explosion dataset collected on smartphones. Explosion monitoring and yield estimation is a vital part of nuclear nonproliferation monitoring. More than 2,000 acoustic explosion data from 26 events were sanitized and curated in collaboration with Lawrence Livermore National Labs. The data curation included adjusting the TNT equivalent yield to effective yield and applying transmission corrections using weather data. The above figure shows the peak overpressure versus the scaled distance of the dataset along with the KG85 reference model. Note the green dots that are significantly lower in peak overpressure at near distances. These are underground explosions that do not have correction factors and have lower energy signals that are transmitted from the ground to the air. The effective yield for each event were separated into three categories of roughly equal sizes, of less than 10 kilograms, 10 kilograms to 1,000 kilograms, and greater than 1,000 kilograms. The reason behind using robust categories is to account for the relatively small dataset for machine learning, which helps alleviate overfitting and to avoid imbalanced classes. Similarly, the height of detonation was separated into three categories of underground, ground, and above ground. A two-layered 1D convolutional neural network was used for the architecture of the model for training the data. A simple model also helps with addressing overfitting issues. The models were trained with both raw pressure data and normalized pressure data to classify yield and height of detonation. 80% of the data were used for training, 10% for validation, and the last 10% were used for testing. The testing results were analyzed by breaking down the data into subcategories of height of detonation and scale distance to gain insight for the performance of the model. Data without underground events were also trained for comparison. The performance of each model is represented in the confusion matrix, where the diagonal entries show the proportion of correctly predicted, and the off-diagonals show the proportions of false negatives and false positives. The leftmost matrices show the confusion matrix for the yield classification for ground and above ground data. The top shows results with the normalized data, and below is with the raw data. The middle matrices show the confusion matrix for the whole data, and the rightmost show the confusion matrix for the height of detonation classification. Overall, we see that the normalized data performs better than the non-normalized counterparts. Also, it seems the spread of false positives and false negatives are about equal. Under the confusion matrices, an accuracy breakdown table is shown. Each model's overall performance, along with subcategories, are shown. For raw data, the model struggles with near-range and far-range data, where near-range performs especially worse. The poor performance of the near-range data seems to be alleviated when the data is normalized. When comparing the height of detonation breakdown, we see that the underground explosions are better categorized when using the raw waveforms, where the underground and above-ground explosions perform better with normalized data. Interestingly, removing underground data seemed to improve the performance of the yield estimation for mid-range and ground data. For the height of detonation classification, we see an improvement in mid-ranged and far-range data with normalization, however worse in near-range. Overall, the performance is better with normalized data. The results of this study will be used for reference in future applications of machine learning methods to the growing database of explosion data collected on smartphones. Lawrence Livermore National Lab had provided the data needed for this study, and mentorship was provided by Dr. Kim. The sanitized data used for this study is in preparation for public release in the near future. Additional explosion data collections are planned with Idaho National Labs and Nevada National Security Site. Normalizing the data improved the accuracy of the yield classification. Near-field and far-field data, where acoustic propagation isn't linear, perform worse in classification. Overall, effective yield and height of detonation were able to be classified in broad bins with limited data. We plan to apply the same methods to a larger dataset, which includes those collected from smartphones. Thank you for taking the time to listen to my poster presentation. Please feel free to contact us for any questions.